let's take a look at these discussion questions you've looked at. So, a dripping water faucet steadily releases drops 1 second apart. As the drops fall, will the distance between them increase, decrease, or remain the same? Now, the first thing I'd like to point out is if you give a 1 second for a water drop to fall, 1/1000. I don't know how big your sink is, but I'm guessing that water drop hit the bottom before the next one was released. So what we're gonna have to assume here for this one is either like milliseconds, or we're just gonna have to assume you have an infinitely deep sink with no air resistance. Okay, so now that we got that out of the way, you can probably tell by my picture that the distance between them as they fall increases. So now we need to go ahead and prove your answer. Okay. So in order to prove my answer, I want to know how far does a water droplet fall in any given 1 second increment. So I want to know what is the displacement. So I want to subtract this x naught over here. So I get a delta x is equal to v naught t plus 1/2 at squared. Now they all are going to experience this portion here. They all have the same acceleration. So this part of the displacement for all three of my water droplets is going to be the same. However, for any given second starting at like this moment in time, they're going to have different initial velocities. So this one will start out at rest. So this number will be 0. This one that's fallen for a little bit already is going to have some initial v naught, and this one that's been falling for a longer period of time, 2 seconds in this case, is going to have a much larger v naught. So the ones that have fallen longer are going to have a larger value here for the longer fall, or the ones that have fallen for a longer period of time, for the drops that have been falling. So not only is the displacement going to be larger because of that, as they go on, that v naught gets bigger and bigger, the velocity it has at when the next drop is dropped. All right, so that's one way I can prove it. Another way I could prove it is I can look at a position versus time graph. And on a position versus time graph, it is going to form a nice parabola like this. Now, when you draw a parabola, and then you say, okay, I'm going to draw the same parabola, but I'm going to start it 1 second later, and I draw that next parabola like that, what you're going to see is that those parabolas do not stay parallel, and they get further apart as you go. And so this is just showing that that distance between them, its x position, gets bigger and bigger over time. Another way we can visualize this is we can drop the first one, and I'm going to call down my positive direction in these graphs, but I'm going to drop the first one, and it's going to have a constant acceleration of 9.8. And then I'm going to drop the second one, also the same constant acceleration here. And so I do see that these are parallel to one another, but when I look at a given interval here of 1 second, I see that the area under the top curve is much larger than the area under the red curve, meaning this is the extra delta x that one is experiencing. This essentially corresponds to this v naught t here. They're both getting this bottom 1/2 at squared, but this one's getting that extra bit. Okay, so you can go ahead and prove it any of those three ways. We'll typically see that on an AP test. It'll be like, is it getting increasing, decreasing, or staying the same? And then sometimes they'll give you a point if you just guess correctly on that. And then you'll get the other point for an explanation. Sometimes you only get the points for the explanation. All right, let's look at that second one there. From the top of a tall building, you throw one ball straight up with a speed v naught and one ball straight down with a speed v naught. Okay. Which ball has a greater speed when it reaches the ground? Which ball hits the ground first? Which ball has a greater displacement when it reaches the ground? And which ball has traveled the greater distance? All right. And I made a note to myself here. I want to answer these in the opposite order they ask them. And sometimes that'll help kind of clarify some stuff. So both of these are starting at the same height. Okay. The one that's going straight down goes that distance, The one that's going up is going to go up a little bit and then further down. Okay, and so because it went up and came back down, this one is going to have a larger distance. But because they both started and ended at the same spots, they're going to have the same displacement. So the one throwing up is going to have the larger distance, and for so that's part D. Part C, which one has a greater displacement? Well, they have the same displacement here because they start and end at the same locations. And then it says, well, which one's going to reach the ground first? Well, you don't have to know physics to know that. If you throw a ball down versus throw a ball up, the one that you threw down is going to hit the ground first. So this one's going to go straight down, and so it is going to hit the ground first. Hits first. Now for the part A. And we needed to set that up for part A to know that the displacements are the same. That's going to be our key there. So part A wants to know which one hits the ground with the greater speed. Okay, so if I set up this equation, v squared equals v naught squared plus 2a delta y. What am I doing? Delta y. Okay, so they have the same displacement. They have the same delta y. So my speed here, the square root of v naught squared plus 2a delta y, they have the same displacement. They have the same v naught squared. One's positive, one's negative, but when we square it, it's going to come out the same. And so because these terms are the same and they have the same acceleration as well, they're both going to hit the ground with the same speed. Again, whenever you do that square root, remember your plus minus. In this case, it's going to be a negative because it will be moving down. And when I say hits the ground, whenever we do these problems, we're always talking about the instant before it strikes the ground. Not like as it hits the ground, oh, it stopped. No, it's the instant before it hits the ground. All right, there's those two discussions.